you don't allow me to share screen. Okay.
So yeah, before you share, let me introduce you. So we will start now, and welcome everybody to the online seminar of the International Institute of Physics. It is my particular pleasure to welcome Dmitry Gorbunov today at our seminar. So Dmitry has graduated from Moscow University, and as a student he joined the Institute of Nuclear Research in Moscow, where he received his PhD and later habilitation. So he remained in Russia, and he worked. He contributed to the work of the group of theoretical particle physics in the Institute of Nuclear Research, which is probably the best group working in theoretical particle physics in Russia. And he was actually one of my professors at Moscow University. And well, this course that he was given with few other guys was probably one of the best I took in Moscow University. And that's one of those courses that, you know, if you learn something that was from that course, and everything that I know about particle physics, I guess, and cosmology, well, much of that I learned at this course. So Dmitry received different prizes in Russia for his work, and in particular, he was elected a correspondent member of Russian Academy of Science in 2016. So his main area of research is theoretical particle physics, and he is interested in particular in application to physics beyond standard model. So today he'll talk about neutrinos and what neutrinos tell us about physics of standard model and beyond. So thank you very much, Dmitry, for accepting this invitation and being with us today. I just remind everyone to keep their microphones muted during the talk. So Dmitry told me that he is willing to accept questions during his talk, and in fact, he would like it to be more interactive. So, well, without further ado, I pass the word to Dmitry. Thank you once again.
Many thanks for your invitation and your kind words. Let me show, where is it? Here it is, I think. Sure. Let me, yes. Where is it? Present the slideshow. Okay. Okay, so I will discuss neutrino physics. We know that in the standard model we have 3 generations of fermions, of metafermions. We have quarks and we have leptons. And in leptons we have charged leptons like electron, muon, and tau, and neutral leptons, which we call neutrino. Okay. And with respect to chirality, we have a kind of asymmetry in neutrino sector because we have left-handed neutrinos and no right-handed neutrinos. This is a difference between, at least from this point of view, difference between leptonic and leptonic sector and the sector of strong interactions, sector of quarks. Okay. Now, in the standard model, well, it is composed in such a way that neutrinos are massless. Okay, and this was a kind of insight from experimental side, because people tried to observe some hint of neutrino masses. No such hint was observed, and they decided that neutrinos are massless. Okay. And now we know for sure that this is not the case in nature. Okay, we observe neutrino oscillations, transitions from neutrino from one flavor to another flavor, and these phenomena are the only phenomena, neutrino oscillations, which point directly at the fact that standard model is incomplete theory. Okay, we need something else, some new physics to explain neutrino oscillations. There are other things we have from phenological point of view, on the phenological side and on the theoretical side. We have dark matter, baryon symmetry, inflation. We have some strong CP problem, gauge hierarchy, whatever, which also can indicate the fact that we need some modification of the physics we have. Okay, but so far, neutrino oscillations is the only direct phenomena which we definitely need to explain to be sure that our particle physics is complete. Okay, now let's describe this is a simple description of neutrino oscillations phenomena. So the point is that we have two bases. One is a gauge basis where we define neutrinos, nu alpha, and the alpha is either electron, muon, or tau. And in this way, we produce neutrinos. Okay, we call them electron neutrinos once it's produced with electron, muon neutrinos with muon, or tau neutrinos with tau, like decay of, say, virtual real W. Okay, they decay into pair, one is electron, another is neutrino. Okay, and this is the name for neutrinos. Okay, and then we have the mass eigenstates, nu I, and the point is that these two eigenstates are not aligned. Okay, so you have a mixing matrix, uh, uh, so-called PMNS mixing matrix, 3 times 3, and this matrix, it's transition matrix between these two bases, the mass basis and the gauge basis. Okay, so naturally through this matrix you can define the mixing matrix in terms of in the basis of neutrino gauge sector, and also it's related through this mixing to the mass eigenstates here. Okay, so mi here are two mass eigenstates of the mass matrix. Okay, we have three neutrinos in the standard model, so three eigenvalues we have. Okay, and well, now we can describe with these definitions evolution of neutrinos. Okay, free evolution of neutrinos. Well, first evolution in time. So suppose we have the neutrino at some point. Okay, and then it just oscillate, obviously oscillate with frequency equal to its mass. Now, if we have the propagation, then this formula should be modified according to this. Okay, so energy here is energy of neutrino, and P here is just the momentum of neutrino. Okay, and assume that, and actually this is always the case we have in real experiments, the situation where energy is much larger in scale than neutrino mass. Okay, so neutrino is always ultra relativistic particles. Okay, then looking at this exponent, we can use the relativistic expansion of momentum in terms of energy and mass, and getting this number. Okay, putting it back, and obtain that the relation between the wavelength at production at 0, okay, at the origin, and the wavelength at distance L. So once neutrino propagate at distance L, its states evolves according to this formula, and this form a kind of effective Hamiltonian. Okay, in the case of neutrino. In spite of the fact that neutrinos are ultra-relativistic particles, this Hamiltonian looks like non-relativistic. Okay, so here is the mass square divided by the energy. Okay, and this shows you how the mass state propagates in case of ultra-relativistic particles. Okay. So now, if you're interested in the situation, you see here is we always, when we detect or produce neutrinos, it's always neutrino in some gauge state. Okay, but when it's propagate, it's a mass state which propagates. So what we do to calculate any process, Well, first you should calculate the probability of to produce a particular gauge state. Then its probability to transfer to some mass state. Then the mass state propagates and then back. Okay, so here is the probability, to produce the to have the initial state neutrino of flavor A, and then flavor alpha, and then observe neutrino as a flavor of beta at some distance L. Okay, so this element describe you how actually what you need just to sum up over all the mass states in between. Okay, so each mass state can propagate according to this formula, and then you should sum up again back to some flavor beta which you're interested in, and then it will describe you the transition amplitude. Okay, so you put all these formulas inside and obtain this type of formula, and then recall the definition of the mixing matrix, and then this is the result. Okay, so what we have here is the transition probability from from alpha to beta. Okay. Now the the probability is just the squared amplitude. Okay, and this is the full formula describing everything. Okay, so this is a so-called vacuum oscillations. Okay, and all three neutrinos participate in this case. Actually, in many cases, in many realistic cases, the situation is such that effectively you need only two states participate. Actually only two states actively participate in the transition. So this is a 2-to-2 oscillation, and in this case, formulas are much easier. Okay, for the transition probability is given by this formula, where you have this difference in mass, okay, mass squared, and here is the mixing angle, okay. L is the distance, energy is E, okay. So the probability to have to so-called survival probability to observe the same type of neutrinos at a distance L is given by this formula, and oscillation length is related to the mass and energy in this way. Okay, so for example, if you have neutrinos of electron volt scale, then say the neutrinos from a reactor have an energy of over the MeV would oscillate at the distance of about 2, 3, 5 meters. Okay, and say if you're discussing neutrinos from the beam, okay, we have the accelerator neutrinos. When we produce the mesons, which decays, and then typical energy of mesons at the level of 1 GeV, then the oscillation length at the level of 2.5 kilometers. Obviously, to to study this physics, to study this probability, okay, you're interested in the situation where the sign is of the order of 1, okay, and then you can measure the mixing angle, okay. But in any case, this is the oscillations in the sense that the probability depends on the sine squared of the distance from the production point where you produce neutrinos to the detection point where you detect neutrinos. Okay. Also, it should be noted that this formula implies a situation where we have the monochromatic source. Okay. I mean, obviously, you can't, be so lucky that to measure the particular neutrino you produce. Okay, obviously you have some kind of source of neutrinos, okay, and they have some distribution over momentum or over energy. And in this case, if you place the detector at particular distance L, then you should average over the energy interval this sine square which enters this formula, which reduce your sensitivity to the mixing parameters. And this is one of the problems when you want to very accurately measure neutrino parameters. Okay. Another thing is that here is L, and so you should either detect the position where neutrino has been produced, or again average over some region if you sum up all neutrinos produced in this particular region. Okay, and this is a similar problem. Well, now, well, it was a kind of vacuum, so-called vacuum oscillations, okay? But actually, neutrinos participate in weak interactions, and because of weak interactions in matter, well, actually, similar to we have in case of photon, for example, okay, propagating in water, for example, yeah. So neutrinos can propagate inside the matter, for example, inside the sun. And because in the sun we have the plasma of electrons, neutrinos can also interact also with this plasma, and in this way gains additional effective potential. So in case of plasma, it's written like this. And because of this effective potential, its effective potential should change the pattern of oscillations. And it happens that at low energy and at high energy, okay, because the effective potential is vacuum potential is inversely proportional to the energy. So at obviously at small energy, this will be dominant contribution, but at large energy, it happens that if you have the situation where the density of electrons is large, like we have in the center of the sun, then this effective potential dominates over the vacuum contribution, and so you have different patterns of neutrino oscillations, and we actually observed this nice effect, so-called Mikheyev-Fenstein Smirnoff effect, and this is the result of the Borexina, for example. Okay, so the probabilities of probability of neutrinos from the sun change with energy according to that to this theory. Okay, so we also observed the neutrino matter effect. Well, sorry. Sorry. Okay. Yes. So now, what we know today, we know because of measurement of this neutrinos pattern, neutrino oscillations pattern, we observed two mass square differences. So-called solar, it's historical name, so-called solar neutrino mass and difference and atmospheric neutrino mass difference. They are related to the fact that, well, two important sources of neutrinos we have here in the sun, the Earth, is the sun, where we have neutrinos, and the oscillations of solar neutrinos was measured accurately, and still are measuring accurately, and they reveal the mass difference of this type, of this size, of about 10 to minus 4 electron volts squared, and also another source are cosmic rays, which produced in the atmosphere mesons, which decays and produce in this way neutrinos, electron neutrinos and muon neutrinos, and we measure the flux of neutrino flux at the Earth, and again, because they propagate differently, we can they also observe that there is another pattern here, and the mass squared here at the level of 3 times 10 to minus 3 squared electron volt. Also, so and in this way we observe two mixing angles. We also observed another mixing angles from results of accelerator and reactor and neutrino experiments, and also some hint of CP phase, a violation of CP symmetry in neutrino sector. Okay. Now,
may I ask a quick question?
In all this, yes, please.
Maybe you're going to explain this, but you showed two numbers for solar and atmospheric neutrinos. So yes. What's the reason for them being so different?
Oh, no idea. You see, it's like say we have in the standard model, say we have 6 quarks, okay, and all these quarks have absolutely different masses, starting from say 5 MeV and 2 175 or 74 GeV for top quark, okay? And there is no any idea why we have this hierarchy in the quark sector, okay? So here we just measure the pattern, the results of neutrino oscillations. I mean, the probability of survival probability, transition probability, and extract these numbers just like numbers, okay? We don't know, in the standard model we have no, the neutrinos are massless. Here is just result of experiments, okay? People try
But
to, when they
both
try
numbers
to
are for
Mhm.
both numbers are for electron and fermion neutrinos. Or
No, 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 no.
oh, okay, so
They are related to the mass eigenstates in a bit more complicated way, and so people describe two situations, two typical situations, so-called normal hierarchy and inverted hierarchy. Okay, so you know, just two mass square differences. Okay, so you have eigenvalues, and you actually measure the difference of squared eigenvalues. Okay, and you don't know the scale, for example, from neutrino oscillations experiment. Generally, you don't know the scale of neutrino mass. Okay, and but people discuss well, naturally when we have this hierarchy, then we can imagine the two situations, so-called normal hierarchy and inverted hierarchy. In the one case is the normal hierarchy, one eigenstate is heavier, and in case of inverted, two heavy states. And the heavy, I mean, in the sense, I mean, again, heavy with respect to what? Okay, all these numbers here is at the level of 10 to minus 2, 10 to minus 3 electron volts. All these numbers are very small compared to, say, the lightest particles we have in the standard model, which is the electron, 500 keV. It's the smallest mass we have in the standard model, which with what we can compare this value actually is probably the energy density of cosmological constant. Okay, so if you take the cosmological constant in terms of energy to the 4, okay, then its value at the level of 10 to minus 3 electron volt. Maybe this is the closest number from what all the numbers we have in particle physics, if you think that the cosmological constant should be in particle physics, okay? And we don't know, I mean, we don't know the nature of this hierarchy. We don't know why these numbers particular of this type. Of course, people, when people describe the modification of the standard model, in particular models, they in particular discuss the situations where, well, these numbers are not, just numbers, but there are some kind of symmetry behind them. Like people, for example, discuss some flavor symmetry in quark sector, thinking about some grand unified theory or something else. Okay, so here is the situation, well, similar, but so far we have no any hints of particular symmetry. This, as I described it, is just some numbers. Okay. Well, but it's hierarchy. Okay, there is a hierarchy. No, not so much, not so much as compared, for example, what we have in quark sector again. But still, there is the pattern is hierarchical. Okay. Now, as to the actual mass. Okay, people also try to to measure once they realize that there is oscillations, and to have the oscillations you need some mass. Okay, then obviously you can try to find the mass in some kind of direct way. Okay, the direct way to observe mass is, say, for example, looking at the tritium decay into helium-3, and if you look at the spectrum of outgoing electrons, and if neutrino has a mass, then there should be kind of bump there, and people try to search for this bump, and historically, some in 80s, people even observed some kind of bumps and some hint of neutrino mass or whatever. But later they measured it more accurately, and there was a limit at the level of 2 electron volt in my institute, and also similar limit in mines. And presently, the best limit on this mass is obtained with the Katrina experiment in Karlsruhe, and it's at the level of 1 electron volt. The Karlsruhe can go further at the level of some tens of electron volts, okay? And this is the results we expect in the future from this experiment. Just to compare this number, okay, look at similar studies, exactly similar studies for muon neutrinos. Actually, it should be muon and should be tau in these cases, okay. Similar study for decay of muon gives you the limit at the level of 17 keV, and for tau decay limit at the level of 70 MeV. Okay, so it's 3 orders of magnitude gap between all these limits because of difficulty to measure, obviously to measure the pattern of decaying muons and especially tau. Okay, so no any hint of direct hint of the mass of neutrinos. Sorry, sorry again. But we have actually very strong limit from cosmology. Okay, I especially use this kind of limits. It's 10 years old. Okay, where we expected that we understand everything in cosmology. And then people looking using the standard concordance model, cosmological concordance model, and nice measurements of baryon-acoustic oscillations and cosmic microwave background anisotropy from WMAP, limited sum of neutrino mass at the level of 0.3 electron volt. Okay. It's because neutrinos actually contribute both to structure formation, to dark to radiation in the early universe, and to dark matter in the late universe. And there are many issues related to neutrinos as a source of some astrophysical process and cosmological process. But at that moment, everything was perfect, and people limited this number at this level. Okay. Now, actually, we have in cosmology, we have various problems with extraction of, for example, Hubble parameter using the late universe data and the early universe data, extraction of some amplitude of matter perturbations and other things, and so people not so sure that similar limits on neutrino mass are very, very robust. Okay, let me say, so they can change by a factor of 2, or when people try to resolve the issues with Hubble parameter, for example, they suggested modification of particle physics such a way that actually neutrino mass can be, relaxed much stronger. For example, now they discuss the possibilities, and when you relax the Hubble parameter tension, and at the same moment have sum of neutrino mass at the level of 3 electron volts, so that the next run of Katrin will observe for neutrino mass. Okay, so everything changed in these 10 years. Okay, during these 10 years. Anyway, then say we don't know the nature of neutrino mass in the sense that it can be either Dirac or Majorana type. Okay, in standard model, all masses are Dirac type. Also, you have particles and antiparticles, you have fermionic number, and you have the baryon number and leptonic number conserved in the standard model. But because of the oscillations, leptonic number are violated. Okay, still the sum of leptonic charges are constant, remains conserved. But still, this option, when people discuss how to modify the standard model to explain neutrino oscillations, results in people realize that it could be two different situations. The neutrino mass should be a Dirac type or Majorana type. The difference is that in case of Majorana, we have no conserved lepton numbers. Okay. And here is just illustration how Majorana mass would work. Okay. This is a Feynman diagram describing the transition of two charged fermions into two charged fermions and two leptons of the same sign. Okay, and this could be say the neutrino's double beta decay, or could be the decay of k plus to mu plus and pi minus, or similar decays of heavier quarks. But here we have this cross which describes the Majorana mass, and you see the errors go from this cross to different directions. This mass violates the fermion number. Okay. And this could be, if you observe this type of process, this would be the indication of the fact that neutrino have a Majorana type mass. Okay. Now, still we don't know anything. We don't know the nature of neutrino mass. We don't know the hierarchy. We don't know exactly the value of the CP phase. But you know, since we have this new sector, we know that it should be modified with respect to what we have in the standard model. It should be much richer. It may be all these answers to this question may be relevant, for example, for the meta-antimatter symmetry. Okay, we know that say if we have the evaluation of lepton number in the early universe before the electroweak phase transitions, then the Falleron transitions can, you know, mix lepton asymmetry and transfer it to the baryon sector. And in this way, through leptogenesis, we can explain the baryon asymmetry of the universe. Okay. Well, also we have in this picture we have additional anomalies. Okay, so we have anomalies where we observe this situation where people studied neutrino oscillations, and at the same at these experiments they observe the results which can be explained like oscillations, but with different values of neutrino mass squared. Okay, so far we measured 2 mass squared and everything is perfect, but once you observe the experiment where this mass difference is significantly different, and here we discuss the anomalies where people consider the situation of having neutrino mass at the level of 1 electron volt. Okay, so you obviously cannot explain this mass difference with 2 eigenvalues obeying the hierarchy of atmospheric neutrinos and solar neutrinos. Well, this could be some kind of indication that the neutrino sector is not complete and should be completed with new light fermion. Okay, so-called people discuss the sterile neutrinos in this respect. Okay, and there are anomalies called appearance and disappearance. Appearance when we have one type of neutrinos at the beginning and another type of neutrinos at the end, and you have more neutrinos at the end than you expected. And the disappearance, obviously, is a situation where you have some well, amount of neutrinos lower than you expected in the standard case of 3 neutrino oscillations. And there are several experiments, several anomalous experiments, and maybe we will discuss them later. Okay. So, well, anyway, all these issues in neutrino sectors must be fixed, not only from the point of view of understanding the fundamental physics. Well, neutrinos are very specific particles. They can penetrate through very heavy stuff. Okay, and because of that, then can be used as a tool to for example, to monitor what happens in a reactor, in nuclear reactor. Okay, they can be used to understand what happens in the center of the sun. They can be understood to understand how the center of the Earth is constructed and what is the distribution of the matter inside, and many other things. Okay, but before using it, we obviously should understand this sector more accurately. Okay. measure all these parameters, understand the situation with anomalies and all these things. And well, the next generation experiments is aimed to do this, obviously. Okay. Now, sterile neutrinos. You see, well, in this case, as I discussed, if you look seriously at the neutrino anomalies, then well, you should understand that you need some more light stuff. One more neutrinos, it cannot participate in weak interactions, and then it should be something else. It should mix with other neutrinos, and in this way you introduce sterile neutrinos. Okay. In the on the other side, even if you have all these anomalies, the sterile neutrinos is one of the option of the physics beyond the standard model. You know, introduced to describe the neutrino oscillations. Okay, so the new fermions are charged under standard model gauge group, and this is the name, the sterile. Okay, the neutrino in the sense that they can explain observed oscillations by mixing with standard model or active neutrinos. And the attractive feature of this type of modification of the standard model is actually you can explain everything within the normalizable theory. So this theory is valid from weak theory, weak scale up to the Planck scale. Okay. Then actually only 2 Majorana neutrinos is needed. Okay, it's just 4 degrees of freedom, and with 2 Majorana neutrinos you can explain neutrino oscillations what we have as we have it today. Okay, except the anomalous part. Okay. Moreover, even with 2 neutrinos, Majorana neutrinos, you can explain actually the baryon asymmetry via leptogenesis, which is also very nice. Okay. With 3 neutrinos or more, you can have the dark matter here and explain the anomaly we observed. With different mass squared. Okay. So the more anomalies you have, if you treat them like the indication of having really light fermions, then you need more neutrinos here. Okay, more sterile neutrinos here. But if you don't look at the anomaly, then the whole picture is also very nice. It's just very small, very very delicate modification of the standard model. And you actually can explain not only neutrino oscillations, but also some stuff in cosmology. But the general pattern is formed in such a way that actually, as a whole, it's untestable. Okay, this model as a whole, this scheme as a whole is untestable because the mass range of the sterile neutrino could be from electron volt scale up to 10 to 14 GeV. Okay. Now, from the point of view of the standard model, the sterile neutrinos looks like you introduced the right-handed components to the lepton part of the standard model fermions. Okay, and well, the Lagrangian again also very simple. Okay, so imagine that you have it's called so-called Fermion Portal. Okay. So you have a fermion which is sterile with respect to the standard model. So it's singlet with respect to the standard model gauge group. Then it happens that as a standard model, you can have the interaction between this singlet and the standard model fields of this type, of Yukawa type. Here is a lepton doublet, here is a Higgs doublet, and here is sterile neutrinos. Okay, so this is Yukawa type of interaction. The parameter here is in front of it. The parameter f is dimensionless. Okay, so this is Yukawa term, and so it's renormalizable. Okay, here is the mass, and I choose the case of my Majorana mass to reduce the number of degrees of freedom here. And you see when the Higgs gains non-zero vacuum expectation value, like we have in the standard model, then this term gives you mass of mixing between the sterile neutrino, this n, and say here is I just take one sterile neutrino, one fermion of the standard model. So here we have this mixing matrix like 2 times 2. Okay, you see it's very simple. And here is this mixing which appears once Higgs gains non-zero vacuum expectation value. So it's very nice. You see the active neutrinos in this case obtains mass because of the same Higgs mechanism we have in the standard model for all other fermions. It's very economic. And then imagine that the off-diagonal element here is much smaller than the diagonal element. This off-diagonal element is called Dirac mass. And then, the mixing is just the ratio of this off-diagonal element to the diagonal element, this theta mixing angle, okay? Then you rotate, go into the mass basis, and then in mass basis you have the mixing. Obviously between active state and sterile state, okay, and theta governs the contribution of the sterile state to the state which interacts, say, with in the participating weak interactions. Okay, obviously, if you have the situation where this mass is much heavier than the electron volt scale, then the one of the eigenstates of this system is sterile neutrinos, and another one is active neutrinos. Okay, and the masses of this matrix are again very simple mass eigenstates. Okay, mass eigenvalues. One is just this mn, and another one is just this m multiplied by the squared of the mixing angle. You see, and the fact that it's squared, it's not just mixing angle, but the squared of mixing angle. If you have the mixing small, then here you have you increase the hierarchy here, and in this way people argued that maybe because of that we observe the so strong hierarchy between uh, mm, neutrino masses and masses of all other fermions. Okay, again, here is 1 electron volt, for example, and in case of quarks, we have a MEV scale, and you see this is 10 to minus 6 hierarchy between them. Okay, so this is a so-called seesaw mechanism, and naturally, if you have we have 3 active neutrinos, and so we expect at least 2 sterile neutrinos, maybe 3, maybe 4, whatever. But in that case, all this formula modified accordingly, and you will have the mixing matrix and mass eigenstates and mass eigenvalues here. And again, you can expect the small mixing. And in this case, many formulas simplified. But anyway, it's just 3 times 3 matrices which enters these off-diagonal elements. Okay, it's very, very, very simple description. Okay. Now let's look at this Lagrangian more accurately. You see here is the mass, here is the Yukawa term. Okay. When I describe them, it would like very natural to introduce them. You see, in the standard model, you cannot write down this type of mass because all the fermions in the standard model carry some gauge charge. In case of sterile neutrinos, they are similar with respect to standard model gauge group, so you can write down this type of interaction. Okay, this type of mass. Okay, so it looks like natural. Okay, anyway. If you look at the whole the whole situation, it's not there are some things to discuss. Okay, first you can if you consider the situation where the Yukawas are very, very small or zero. Okay, they are so-called just the free fermions. Okay, so you introduce the free fermions. You can discuss the cosmology, for example, in this case, but they are also obviously not you can call them sterile okay, neutrinos, because you have no, in that case, you have no mixing between these fermions and the standard model neutrinos, okay. But still, people discuss this type of models as well in terms of for the cosmology, okay. Now, if you put here this mass term to 0, okay, then sterile neutrinos and active neutrinos will form Dirac neutrino. Okay, in this case, if you look here, okay, if you look here, imagine that here we have 0. Okay, then you still have the masses in neutrino sector, so you can still explain oscillations. But in this case, obviously, you need to tune this parameter of f to 10 to minus 11 to have 1 electron volt neutrinos. And then you see it's very, very tiny coupling. And then it's very difficult to observe some other hints of presence of right component of neutrinos. Okay, this is the option. Okay, it's more boring case, but this is the option. It's well, people sometimes call that well, you can easily explain neutrinos just by introducing right-handed components. Yes, it's true. You can easily explain neutrinos by introducing right-handed components if you put this mass to 0. Okay, but it's a very boring situation, of course. Okay. Now, well, what we discuss here is the situation where both terms are non-zero. Okay, it looks like natural. Yet it's important to understand that when both terms here are non-zero, when you introduce this type of matter to the standard model, we violate lepton symmetry. Okay, the point is that this Majorana term violates lepton symmetry, and when both of them are present, we we transfer this violation to the standard model. This is an important thing. Again, from the point of view of neutrino oscillations, we don't need to introduce this type of terms. Okay, just Yukawas would be enough. However, all the masses of the fermions in the standard model are non-zero, so we expect that maybe it would be natural to have this mass non-zero as well. But then we violate lepton symmetry, while in the standard model, lepton symmetry is conserved. Okay, this is an important thing to understand about this model. At the same time, once we do this, we get very interesting cosmology. We can explain the baryon asymmetry of the universe with leptogenesis, and this is interesting. Okay. Well, now actually the simple case, the simple modification of standard model when we can describe the neutrino oscillations would be like this. It was suggested by Weinberg. It's dimension 5 operator. Here is the lepton doublet. Here is the Higgs doublet. And once Higgs against non-zero vacuum expectation value, here we have the max for the neutrinos. Okay. And you see, if you look now at our model and consider a situation, for example, where sterile neutrinos are heavy, then from these Feynman diagrams, we obtain exactly the same operator. So this is a kind of UV completion for the dimension 5 operator suggested by Weinberg. Now, looking even at the relation between the mass of active neutrinos and sterile neutrinos in case of just one generation of active neutrinos and one generation of sterile neutrinos, we observe that, well, obviously, you can fix the mass. Okay, you can take heavy mass and small mixing, or a bit larger mixing and smaller mass. Okay, so just from this relation, you cannot fix at which scale you expect new physics, and this is a problem with many models which suggest the origin of neutrino mass. Okay, you see, we cannot point at the particular scale of new physics where we can expect some real stuff, some new particles. and you know, again, it's a kind of a natural situation here if you look at this formula. And in case of three generations, okay, then you have this type of relation between mass matrix and this Yukawa matrix. And in this case, the situation is even worse, because obviously you can have the situation where, say, not only the scale of Yukawa couplings are not fixed, okay, you always can have Yukawas of order 1, but with some special symmetry, you can tune them in such a way that in spite of the fact that Yukawas of order 1, the mass eigenstates, or the mass eigenvalues are very, very small, okay? Well, it's interesting from the point of view of phenomenology. When you cover for the one, you can expect some signal, okay, but you can have you can predict the rate, okay. Now, just to illustrate this with some kind of sketch here, here is the scale. Horizontal axis here is a Majorana mass in GeV, okay, and it can go from 10 to minus something, 10 to minus 13 GeV, to 10 to minus 14 GeV, okay. And here is Yukawa couplings, okay, the scale of Yukawa couplings, again, just scale. And here is the triangle where everything is perfect with respect to explanation of neutrino mass within this ISO mechanism, okay? And you see, well above you have either strong coupling, okay, or neutrinos mass are too small or neutrino mass too large, but this range, this region is absolutely allowed, and it spans for some 10 orders of magnitude in mass and 13 orders of magnitude in Yukawa couplings. Okay, everything here is perfectly agreement with observation, and this is the the problem. It's not very predictive, and so many things depends. But anyway, though many things depends on the mass value, still we have another option. Another option is to have just two sterile neutrinos or three sterile neutrinos. Okay. And even in this case, we have many interesting things to explain within this pattern. Say, we to explain neutrino oscillations. Okay, so far we observed two squared mass differences, three mixing angles, and some hint of CP. Okay. But generally, if you have all three neutrinos mass eigenvalues non-zero, then in the standard model is the active neutrino sector. You have nine parameters. Okay. Uh, well, again, so far it's not excluded that one of eigenvalues is zero. Then we have 7 parameters. Okay. But with two sterile neutrinos, we have 11 parameters. And with three sterile neutrinos, we have 18 parameters in this model. Okay. And so you see we have a freedom. So we can tune some parameters in the way we like. And it happens that even with 11 parameters, we can tune them in such a way that to explain, for example, lepton asymmetry of the universe. Okay, if you have two sterile neutrinos, you have two non-zero mass and active neutrino sector. If you need to have three non-zero mass and active neutrino sector, you need three sterile neutrinos. Okay, they one-to-one correspondence. Okay. So generally we have 18 parameters. With nine new parameters, you can do many things. Okay, and this is the freedom we have, still working within the paradigm of CISO mechanism. And well, then there are many things you can do. For example, you can do the Biogenesis or dark matter. Okay. Now I have just not so many, some 15 minutes, yes, or 10 minutes, yes.
Yes, more like 10 minutes.
Okay. So let me just skip this biogenesis, and it's very interesting, and there is serious progress in the recent years here, and people studied the options to search for sterile neutrinos if they're in GV range, and one of the options here is to have the KV scale dark matter. And the interesting thing here is that these sterile neutrinos can decay into neutrinos and a photon, and the people search for this type of signal, looking at the X-ray spectrum from the galaxies and galaxy clusters, and even sometimes observe some kind of signatures, arguing that that could be because of the sterile neutrinos. And now the new apparatus can actually probe the whole space of dark matter here. But well, just let's concentrate in the at the 1 electron volt sterile neutrinos, at the anomalies. Okay. Let me say that imagine that on top of this 3 neutrinos we have one more. Okay. And the motivation here is then once you observe the result of oscillation in such a way that the mass square difference is much bigger than the mass square difference observed from solar neutrinos experiments and from atmospheric neutrino experiments, then you need something else. Okay, so you need to introduce one more neutrino in electron volt sector. Okay, to have sterile neutrinos with mass in electron volt region. Okay, then obviously in all these experiments, these sterile neutrinos will also be relativistic. And all the details, all the descriptions of the process involving sterile neutrinos are the same. They just oscillations. Okay, so we should just modify somewhat the formulas we used previously to describe oscillations. For example, the oscillations probability would depend on the mixing between the sterile neutrino stuff and the electron, muon, or tau sector, and the transition probability. Would they looks again just the formulas describing 2 to 2 oscillations. Okay, however, the relation between the mixing angles and the parameters describing actual mixing between sterile and active neutrinos are a bit different. Okay, so here, for example, transitions from electron to muon, and if sterile neutrinos contribute there, then the corresponding mixing is just the product of the mixing between sterile and electron and sterile and muon. Okay, so you describe the situation like electron transfer to sterile and then sterile to muon neutrinos. Okay, well, and then also it can be in case of survival probability that some electron neutrinos, for example, transfer to sterile and then disappear. You cannot measure the sterile stuff, because all your measurements are based on the understanding that neutrinos participate in weak interactions, and you can either measure something like electron neutrino or something like muon neutrino, something like tau neutrinos. Okay, you cannot measure the sterile contribution, so it's disappearance. Well, there are anomalies. For example, the very well-known, very old LSND anomaly, where people observed the anomalous appearance of electron antineutrinos. Okay, so the pi indicates to muon and mu, and then muon into electron anti-mu, and then you observed this type of process, which you interpret like a scattering of electron antineutrinos on the proton. Okay, and people observe some anomalous effect at the level of 4 sigma. And here is the region of parameter space. Here is the mixing, and here is the mass. And here are various limits from various experiments. Exclusion regions are here. Okay, and here is the anomaly, the anomalies of this LSND. Okay, people suggested specific dedicated experiment to measure this anomaly, mini boon. And first, they claim that they don't observe anything like LSND and place some limit. But at the same time, they observe some anomaly by themselves at low energies of recoiled electrons. And but later they claim that they observe the anomaly in accordance with LSND. And it's actually both in case of anti-nu mu to anti-nu e, and also in case of nu mu to nu e, so both in neutrino and anti-neutrino sector. Okay, so they operated with both beams. Okay, well, it's called the anomaly because there are some combinations of results of other experiments which claim that the region is excluded. For example, like here is in this paper, and this green region, the LSND anomaly, is excluded by combined analysis of Minus and Diabay. Okay. Well, still this is anomaly. Okay, it exists. Okay, and there are other anomalies. For example, when people searched for oscillations from neutrinos from the sun. Okay. And this is example from experiment from my institute, so-called SAGE experiments. So in the sun you have production, you have scattering of two protons, okay, with production of neutrinos, and then here at the Earth, people use the gallium to produce germanium and electrons, and then they expose a lot of gallium. Target of gallium, and then extract this germanium nuclei and count them, and this way calculated the flux of neutrinos from the sun. Okay, and similar experiments with similar technique was the Galax experiments in Italy. And before the experiment and after experiments, they try to calibrate their technique, okay, their experiments, calibrate with artificial sources. And it happens that this calibration reveals the anomalous results. So they have, they have a lack of neutrinos in both experiments, and this is so-called gallium anomaly. Okay. If you combine the SAGE and Galax results, then the gallium anomaly would prefer the mixing at the level of 0.3 and the mass at the level of 2 electron volts. Okay. Now a reactor anomaly. Some 10 years ago, people recalculated the flux of antineutrinos from reactors and observed some, some 6% deficit to the antineutrinos from the reactor. Okay, actually this is very seriously. Okay, you can argue that it's because the lack of material uranium inside the reactor. Okay. But here is what you expect. Here is this red stuff, okay, and here is the blue stuff, and here is this 6% disagreement, and here is the various results, various measurements made with different reactors. And people combined this together with the helium anomaly and pointed at the mixing angle at the level of 0.1 and the mass at the level of 1 electron volt, like the gallium joint reactor and gallium anomaly. And this could be because we need one more neutrinos, so-called sterile neutrinos. Okay. And here is the new measurements by Reno, Diabay, Double Shoe. Well, actually now they, on top of that, they also observed some kind of unexpected bump at 4 MeV, not so large, but still recognizable. And the origin of this bump is still debatable. Okay. And mind, this is the flux from nuclear reactor. Okay. Now, well, there are new experiments. Obviously, this is a very hot subject. There are new experiments. Here is the NEOS experiment, and here is the DANCE experiments. Here is the Korean, here is in Russia, and they use the very powerful reactors. And well, again, while they excluded some part of model parameter space, both results have the most probable region, which is mostly consistent with the results, and this region implies non-zero mass and non-zero mixing. Okay. Moreover, they are close to each other, and the combined results reveal some kind of 3 sigma anomaly, pointing at the now much less mixing, but still recognizable, and the same mass of the 1 electron volt. People try to, to combine various results of various experiments, because you see, if everything is in agreement, then it's not an anomaly. This is still anomaly, because if you account for all the experiments, then sometimes you will have the situation where the I say disappearance and appearance experiments present you different numbers. And for example, here is experiments where you have anomalies in disappearance, and here is this red line. Okay, you have you don't need actually the sterile neutrinos to explain the results of this disappearance experiment. At the same time, this blue line indicates the LSND region, and you see they are not consistent with this at the level of 3 sigma. Still, you can combine them, okay, saying that, well, maybe it's just the just the statistics, and they should all sum up everything, and then this cross here indicates the combined results. Okay, the global fit. Well, now, quite recently, there was other experiments. The prospect and stereo revealed no any hints of the sterile neutrinos. Okay, they used the compact reactors. It's not powerful, but it's scientific reactors. Okay, and similar neutrino 4. But in case of neutrino 4, they claim that they observe some hint of sterile neutrinos. Okay, it's at the level of well, depending on the interpretation, from 3 to 4 sigmas. Okay, here is this blue region. Well, the statement is that it's still consistent with the results of other experiments. Okay, but this result is very anomalous. It implies a very large mixing. Okay, and it implies a very large mass. It's the level of 7 electron volts, so it's 2.45 electron volt if you calculate in terms of mass, of sterile neutrino mass. Okay, and this is very now well, actually, this number is consistent with the gallium anomaly, for example. Okay, if you write down them on the same plot, here is region 1 sigma region preferred from the gallium anomaly, and here is neutrino 4. So if you combine them, it will be more than 4 sigma anomaly together. Okay, so if you believe to both experiments, to do both anomalies, then it's something like 4 sigma signature, 4 sigma evidence for the sterile neutrinos. Still, we have there are some problems with all these experiments, reactor experiments. Well, if you have, you see, because if you look at the oscillation formula and claim that you have some evidence for electron volt sterile neutrino, analyzing the neutrinos from reactors and the energy at the level of 2, 4, 5 MeV, then the oscillation length at the level of 2 meters. Okay, and you have the reactor, and the reactor is not a compact source, so you should average over the reactor region, and this is the problem. So that's why, for example, the scientific reactors are better than the reactor we use in the power plants, because they are compact, and the situation is easier there. Still, you need to accurately measure the energy, otherwise you have the same problems I just described with when we wrote down that formula with oscillations. Okay, so it would be better to have the monochromatic compact source just to test everything. Okay, and in this case, it's another option. So people suggested the experiment in my institute called a Baksan experiment on sterile neutrino BEST, where they have very compact object, compact source of artificial source of neutrinos at the level of 3 megacurie. Its size at the level of 10 centimeters. It's very, very, very small. Okay, so there are 2 vessels filled with gallium, and when neutrino propagates through the vessel, they can interact with gallium, change it into germanium, And then if you extract germanium in this vessel and in that vessel and compare the numbers, you can check the oscillations. Okay, the idea that some neutrinos disappears, and the scale here is at the level of 1 meter, so you're exactly sensitive to that to that sterile neutrino stuff. Okay, the data taken was in July and from July to September. Well, almost 2 years ago. Okay. And it looked like that. Here is this, the largest vessel, the smallest inside. Here is the artificial source, and here is its actual size. Okay, it's the box inside. Here is, and it actually even smaller than that one. Okay, so it's very small. And well, the if this experiment confirms the neutrino 4 results, then it will be more than 5 sigma discovery of neutrino oscillations. Okay, if it's consistent with the result of neutrino 4. And let me just say that they promise to announce the results very soon, maybe during this, either in May, but most probably during the neutrino conferences in summer, and maybe this will be the discovery of new particle in the standard model, unexpected with respect to what we expect from the, for example, for Higgs, which we hunted for 50 years. Here is this unexpected particles, and it will be very interesting from the point of view of both particle physics and cosmology, and understanding of how the model building should be, should be organized, should be based, because well, there are not so many fundamental theories why we should expect light particles in the hidden sector at the same of the same mass, similar mass as we have in the active neutrino sector. So thank you very much for your attention.
Well, thank you very much, Dmitry, for your very interesting talk, and you kept the most interesting stuff for the end, so it would be harder for me to stop you. But anyway, so if we have any questions, please raise your hand or sign up in our chat to ask the question. In the meantime, let me ask everybody who can turn on cameras to turn on the cameras right now for us to make a picture of all the participants. So Baldolino, please let me know when you are done with the picture. There was one request from the audience about the slides. Is it possible that we publish the slides after your talk?
Yes, of course.
Okay, so I think we can do this on the website, on the web page of this talk, on the website of the institute. So I don't see any request for questions. So I would like to maybe come back to the question I asked earlier, and my confusion was basically that's probably very basic question. So about solar neutrinos and atmospheric neutrinos. So why do you measure two different numbers? What is different in two experiments that makes you measure different numbers? So I understand that the parameters of the standard model or physics is one thing, but what is different in experiments that make you measure different numbers?
Well, in case of solar neutrinos, okay, what you measure is you measure neutrino, say originally, okay, you measure electron neutrino, okay. So you can directly measure, for example, muon neutrino, because to make sure that it's indeed muon neutrino, you expect to produce muons in the inverse process. And to produce muon, you need much higher energy than we have in fusion in the sun. There we have, say, from 100 keV to several MeV, okay? So you can have this direct measurement, okay? Of course, you can measure neutrinos via, not via charge current, but via neutral current interactions, okay? But then you're not sure whether it's a tau neutrino, for example, or muon neutrino or electron neutrino. You measure the sum of them, So you cannot measure the differences. Okay. So in the original neutrino, solar neutrino experiments, you measured only disappearance of electron neutrinos, and that was a kind of puzzle. I mean, you can interpret these results either as a statement that you have oscillations and disappearance of neutrino into and transfer of neutrino into some other particles. Okay, so for example, muon neutrino cannot transfer gallium into germanium. Okay, but you can also say, well, when you predicted your flux, electron neutrino flux, you based on some model of the sun. Maybe the model is not correct. Okay, and actually, this is one of the way to check the model of the sun. And now, actually, for almost 20 years, we have the problem with the solar model because some observation we have inconsistent with each other. I mean, in case of the sun, at the level of several percent, but still they're inconsistent. Okay, so there is a problem with this solar model. Still, it's most probably not related to neutrino oscillations, okay? Because now we know that neutrino oscillates from various other experiments. In case of atmosphere, you produce pions and kaons, which decay and produce muon neutrinos, okay? And muon neutrinos can interact. They have enough energy to produce muons, and you can measure that they indeed muon neutrinos, okay? But at the same time, they can oscillate to other type of neutrinos, okay? And you measure the other type of neutrinos as well, okay? Then you just compare the numbers, and it happens the numbers are different, okay? So the mass squares are different, okay? It just happened, okay? Now, to be honest, that just funny thing. It just happens that actually not all particles of the standard model we observed so far. There is one, namely anti-tau neutrino, which we so far didn't manage to observe directly. I mean, we didn't observe the situation where you produce anti-tau, okay, and that would be the indication of tau neutrinos, okay. So in case of solar atmosphere, originally it was because of the difference of the kinematics. So you can produce muons, okay, and then you interpret this like oscillations of electrons to something else. Okay, actually within these two patterns, that could be either to muons or to tau neutrinos. Okay, well, once again, when you do your combined fit, okay, global fit, then you use the whole formula where all three neutrinos participated, okay, and then you have three eigenvalues, and people people actually now when they extract the parameters in neutrino sector, they observe the difference between the preferable regions in case of normal hierarchy and inverted hierarchy, okay. But in many experiments, when you look at this complicated formula, you understand that the parameters with the numbers entering these formulas, it enters in such a way that some parts there are negligibly small. And then effectively what you observed is oscillations between two stuff with some effective mass and some mass difference and some effective mixing differences, mixing angle, okay. And in case of solar neutrino, you can look at the formulas and observe that they reduce to 2-2 oscillations. And the case of atmospheric neutrinos also, it reduced to 2-2 oscillations. But for example, when you discuss many things like, for example, CP violation, okay, now people say that, looking at the, for example, T2K results, This is the results. This is accelerator, experiment accelerator neutrinos, and then search for CP violation. Then you need to use the whole formula to observe the hint of CP phase. All the terms there are important for this analysis. And so it's not just simple to do oscillations.
Okay, thank you. I think you answered more than one question, but it was very good. Any other questions?
Can I ask a question, please?
Yes, please, Edison.
Could you consider any of these issues in neutrino at finite temperature? I mean, in situations in which you have thermodynamic equilibrium.
In the early universe, you mean?
Could be at the early universe. Could be.
Yeah. In the early universe, people discuss, for example, when they predict the relic abundance of active neutrinos, then they consider neutrinos as a thermalized species, and well, it's thermalized just because of the weak interactions. But when you have, for example, this sterile neutrino stuff, okay, by itself, it doesn't participate in any interactions. But because of the mixing with active neutrinos, they also should be produced in the early universe and should be present in the primordial plasma, more or less the same amount as electron neutrinos or muon neutrinos or tau neutrinos. Because of the mixing, we discussed, for example, in case of anomalies, this mixing is quite large with respect to that processes. And this is the important thing for cosmology, because the standard cosmology is inconsistent with additional neutrinos, and you need to modify something else to say that it's consistent with cosmology. Okay, but cosmology is anyway, it's not the direct thing. If you observed sterile neutrinos in experiment like BEST or like DANCE or like LSND consistently, okay, it's not just anomaly, but all the experiments, neutrino experiments, agreement with that, then it means that our understanding of the early universe cosmology is not correct, and we should modify it, taking into account this neutrino. Okay. Just maybe just let me show. Just let me show the situation. For example, can you see this? Do you see this? My slides?
No, I think you
No.
stopped sharing them. You have to share them again.
Okay. Anyway, it doesn't matter. I mean, people now discuss various modifications. For example, if you introduce, say, interaction between sterile neutrinos themselves, okay, in that case, you change the prediction of their abundance. If you introduce, say, some scalar field, you see the mass of the sterile neutrinos just by hand, okay? And you like to have mass because of some Higgs mechanisms. And instead of that, you could prefer interaction between some new scalar. It cannot be Higgs because it should be sterile, okay? It should be singlet with respect to standard model gauge group. So new scalar and this neutrinos. And then because of that interaction, this scalar in the early universe can change you completely the production of the sterile neutrinos. You can suppress it or enhance it. It really depends on the dynamics of the field, and people discuss this. It's quite rich literature on that subject.
Thanks a lot.
Okay, any other questions? I maybe want to ask some questions to summarize. In the end, you talked about these best experiments and the possible new discovery. So since it was a bit quick, so that it means that it will be discovery of a new neutrino, sterile type. And will it help to, let's say, fix any of the parameters of the, let's say, uncertainties related to sterile neutrinos, models with sterile neutrinos?
Yeah, you see, the problem with these anomalies, one of the problem with all these anomalies is that you can explain them with just one sterile neutrinos. If you would like to describe all of them, LSND, mini boon, reactor, gallium. Now I didn't mention, for example, there are some anomalous results from ice cubes. They also observed some kind of hint of light neutrinos in the atmosphere. Okay, you can do it just with one sterile neutrinos. You need more, and in that case, it's more difficult from the point of view of cosmology. But anyway, it means that at least part of this, I mean, if there are some parts of these anomalies which can be explained with this sterile neutrino, if it's present, if it's in that region I explained. The anomalies in, say, electron neutrino sector can be explained, okay, in that case. So because all of them, these reactor anomalies and gallium anomalies, they are disappearance, okay? So you expect some amount of neutrinos in case of gallium anomaly, or antineutrinos in case of reactor anomaly, but see less amount. And you cannot explain this lag just through oscillations in active neutrinos. The parameters not enough. The oscillations happens, but not sufficient. Okay, so you introduce one more source of disappearance, and this is direct disappearance in the sterile neutrinos. Okay, and this case, this thing you can explain if it's sterile neutrinos, but with the same parameter you can't explain, for example, the LSND anomaly. The interpretation of LSND anomaly is that you have, transitions from muon neutrinos, from muon antineutrinos to sterile neutrinos, and then from sterile neutrinos to electron neutrinos. So this this double step you can't explain. Two-step process you can't explain with the parameters preferred from the reactor neutrino anomaly or gallium anomaly. You need something else, or say that this is just anomaly, this is a fluctuation. Okay, all these anomalies can be just statistical fluctuations or some, inaccuracy in experiment or something else. It does not mean it's not 100% hint at the physics beyond the standard model. Maybe it's the hint that we overestimated our accuracy in neutrino experiments.
Okay, thank you very much. Thank you very much again for accepting this invitation. Well, let's say there's actually one more question from Yosara. What is the overview of the ship bounds for dark matter and neutrino detection? I'm not sure.
Sorry, ship bounds?
Do you know anything about ship bounds for dark matter and neutrino detection? I think SHIP is an abbreviation probably for some experiment, SHIP. Yosara, can you ask your question?
No, no. The ship is not for
hydrogen particles.
Wait. Let me.
Just remember that we don't see your screen at this.
Okay. Yeah. Now, is it okay?
Yes.
I know the ship, which is a project. Okay. Here is this limit, but it's not a limit on the dark matter. It's a limit on the heavy sterile neutrinos, which say, for example, in case of, for example, new MSM model responsible for leptogenesis. Okay, here is the GV scale. The GV scale is not preferred from the dark to explain dark matter. To explain dark matter, you need a KV scale, and the third particle, third sterile neutrino should be in KV range. but it cannot be directly probed by the ship experiment or any other experiment, because these experiments are experiments which are looking for the decay of these particles, okay? And KV stuff can decay only into neutrino or neutrino and the photon, and it's quite difficult to measure the KV, just KV photon in this type of experiment. I mean, it's another stuff. Dark matter is better to measure, to search for with X-ray telescopes, okay, or in other way, in any other means. For example, people discuss one of the stage of the Katrine experiment, the future Katrine stage, as a measurement and the search for sterile neutrino in keV range, okay, but it's not the ship. Ship is for searching for heavier sterile neutrinos.
Okay, so I guess there is no more questions. Thank you very much again to everyone who participated, and especially to Dmitry for giving us this wonderful talk and reminding that there's still a whole universe of neutrino physics which needs to be explored. Okay, we'll see you once again next week with more seminars from the Institute.